Hey guys, Miss Marusic here, and in this video we're going to talk about some last formulas having to do with electrochemical cells. Now I've put on here a picture of the last few formulas on our formula chart. Now a couple of these should look familiar, we've worked with them before, but there's two on here that are new. We have that our Gibbs free energy is equal to negative NFE. And we also have this equation of I equals Q over T. Now, both of these equations have some variables that we really haven't worked with yet. And so the nice thing that the formula chart does is that it tells us what these variables represent. And so that makes them a little bit easier to work with. So the first calculation that we're going to look at is the delta G equals negative NFE. And the nice thing about this formula is that it uses some variables that we are already familiar with. Delta G, of course, is Gibbs free energy, which tells us information about thermodynamic favorability. And this E with the degree symbol is referring to the standard cell potential. And so here's that connection between my thermodynamic favorability and my positive or negative nature to my volt value. And so we've kind of already talked about the connection between these. If you remember back in a previous video, we talked about the fact that when delta G, our Gibbs free energy, is negative, when our reaction, our process is thermodynamically favorable with a galvanic or voltaic cell, that we should see a positive value for the volts of the cell. And if you really think about this equation, then that should make sense. If this volt value is positive, when I apply this negative at the front, that will get me a negative value for the delta G. The same thing would go if we had the reverse in play. If we have a negative value to our volts, and remember that happens when we have a non-spontaneous cell, an electrolytic cell, what would happen is the negative of the volt value and this negative in the front would combine to give a positive. And so you end up with a positive value for our delta G, which as we know is thermodynamically unfavorable. So again, we've already talked about the connection between those. What we're going to do now is actually do some calculations with them. Now, these other two components in this formula, the N represents the number of moles, just like we saw in Pivnert. However, here we have to be careful of what kind of moles we're dealing with. Here we are dealing with the number of moles of electrons that were transferred in the balanced net ionic equation. So we've got to make sure that we balance that net ionic, that electrons lost and electrons gained by our two processes are equal, and then we can take that number of electrons and apply it to this equation. Now, the F is something called Faraday's constant. And on your formula chart, you will see that it gives you this value, that Faraday's constant is 96,485 coulombs per mole of electrons. And so that's why this N has to be moles of electrons, so that that unit can cancel out with our Faraday's constant. All right, so with that said, let's see an example where we have this in action. And so we have an example here that says we have a fuel cell employed by NASA on spacecraft, uses hydrogen and oxygen under basic conditions to produce electricity. So again, we're producing electricity here. So that means we have some sort of galvanic or spontaneous cell, more than likely. And then it says that the water produced can be used for drinking. And it gives us our net reaction of our process below. And they give us two half reactions here along with some volt values for those processes. And the first thing they want us to do is to calculate the standard potential of the cell at 298 Kelvin. And so what I need to do is I need to figure out which of these half reactions do I need to reverse. I always know that I need to reverse one of them, because if you notice, both of these have the electrons on the reactant side, and so that means on both of these they would be a reduction. And I know they can't both be a reduction, so we're going to have to flip one of them. So I'm going to use my overall balanced reaction over here to help me do that. I notice that H2 is only found in this first equation. However, I notice that not only is it on the wrong side, but I also need to double it. And so what I did is I rewrote this equation, making those two changes. I reversed the equation, so now this H2 and hydroxide are on the reactant side, and the H2O and the electrons are on the product side. But the other thing I went ahead and did was double it, okay? So then I did the same thing with the oxygen, but here the oxygen was on the correct side, and so I just rewrote this equation as is. And when I do that, if I notice, what happens is that our 4 electrons on either side would cancel, the 4 hydroxides on either side would cancel, and 2 of the waters would cancel on the reactant side and on the product side, leaving those 2 waters on the products. So you can see that gives me my overall equation. Yay! But now let's talk about those volts. Even though I doubled that first half reaction, remember, I don't ever double or triple our volts. The volt value never gets multiplied by how many coefficients I had. It just stays the same, with the exception that I might need to flip the sign. And here, since I flipped that reaction around, I would flip my sign. But again, never ever multiply those volts values. The only thing you're going to do to those voltages is change the sign. That's it. Okay? So then the 0.40 for my second half reaction, that would remain as is. So to get my volts, I just simply add those up and get my answer. Easy peasy, right? And I can kind of double check this here. I noticed that it came out to be a positive 1.23 volts, which means this would be thermodynamically favorable. And if I thought back, this said it produces electricity, not that it used it. And so that would make sense if we're producing electricity that our process would be thermodynamically favorable. It would be spontaneous and a galvanic cell. So the next thing they want us to do is to actually calculate our free energy change, our delta G, for that net reaction. And so this is where I'm going to use our new equation to do so. Now, when I plug into this equation here, I've got to be very, very careful on units, as always, okay? So first off, the negative number of moles here is going to be the number of moles of electrons that was exchanged up here. Now, when I had this all balanced, remember, there were 4 electrons that were gained and 4 electrons that were lost. That 4 electrons is what goes in here. So be really careful. The reason why I went ahead and did that whole balancing my reaction thing out is so I can make sure that the electrons lost and gained, that number was what I plugged in here. So you are going to have to make sure that you have a balanced net ionic equation to really figure out what that number of moles of electrons is that goes there. Okay. Now, F is our Faraday's constant. So I did my 96,485 coulombs over moles of electrons. So now my voltage gets plugged in last. That's a positive 1.23 volts. Now I want to talk about units for a second, okay? There's an equation up here, even though it's really kind of on the other side of things, that says that 1 volt is equal to 1 joule per 1 coulomb. And so what I did here, so I can see the units canceling out, is I showed that that volts would be equal to joules over coulomb. And so now I can start to see how those units would cancel. Moles and moles cancel out. Coulombs and coulombs cancel out. And so that leaves me with a unit of joules. So then all I have to do is plug in this math and solve an answer. I did round here to 3 significant figures. Since my voltage had 3 significant figures, that seemed appropriate. And so I rounded it appropriately with that unit of joules. Now, it did come out negative, but think, it should have come out negative, right? We had a positive number of volts. And we said when the voltage is positive, when we have a positive E cell, that means we are thermodynamically favorable and it's a galvanic cell. Well, for thermodynamic favorability, I should have a negative delta G. So all of these signs match up with what I was predicting it to be. So you want to make sure that all of that hooks together. Now, remember, it is very common to report delta G in terms of kilojoules. And so you could convert this into kilojoules very easily. However, I will tell you this, if they don't specify a unit to report in, just leave it as the unit as is and report that joules and leave it there. That way you're not worried about making a mistake when you're converting back and forth. I think a lot of times it's easier just to leave that unit as is, and that way you don't have to stress about it. All right, with that said, let's go ahead and look at our second equation on the next page. Now, our second equation was I equals Q over T. And I went ahead and re-put on here that picture of the formula chart. I is representative of current, which is in amperes, which often gets abbreviated as amps, or you could just abbreviate it as A. So there's all kinds of abbreviations that we see for that. Okay. Q is going to be charge. That's your coulombs value. So it's the same coulombs that we've been dealing with in other places. T is going to reference the time in seconds. Now, before I talk any more about this formula, I actually want to talk about the scenario where we usually use it, and that is with electroplating. Electroplating is the best practical use that we have of an electrolytic cell, of a non-spontaneous cell. And the way that it works is that I would have some piece of metal that I'm trying to use that metal to plate something else. And so I would have this as my anode. This desired metal was going to be my anode. And what I'm going to do is I'm going to put another object over here that I want to plate that metal onto. So like, for example, we had silver in this picture, and we want to plate silver onto the outside of a spoon. Okay. Now, in order to do this, you notice we do have a voltage source, so some sort of power source like a battery. Okay. So this is going to be for an electrolytic cell. What's going to happen in this process is that our voltage source is going to drive the electrons to go from our metal piece, from our anode, to this other object, to our cathode. And when it does that, the metal is going to do something interesting. It is both going to oxidize, lose electrons, so we're going to go from here, silver atoms to silver ions. And then the metal is also going to reduce. So those silver ions are going to reduce back to silver metal, but now it's going to be on the other electrode. And so what we want to do with these types of questions is we want to figure out how much current is running through this, or use the current to do a calculation. And we want to figure out how much time it's going to take in order to plate a certain mass of metal on this other object. Now, obviously, the longer we let this cell run, the more and more of that metal gets plated onto our object. Okay, so again, our goal here is going to be to determine the actual mass of metal that is being plated. And to do that, they are going to give us the current that is flowing in the cell. They're going to give us the I value. Now, what's going to be interesting here is that that means this current of Q over T, the coulombs per time, is actually going to be used as a conversion factor. Most of the time, we're not actually solving this equation. We're using that equation as a conversion step in our work. Okay, and the way that that would function is that the current is in the unit of amps, but amps can be rewritten as coulombs per second. And you can see I've done that down here. If this this current is in amps, Q is coulombs, time is seconds, that would mean that our amps value is equal to coulombs per second. And so again, we're going to use that as a conversion factor. Now, the other conversion factors that we're going to need is that we're also going to use our Faraday's constant, our 96,485 coulombs for 1 mole of electrons. Okay. We're also probably going to need to get between moles and mass. And remember, how do we get between moles and mass? Molar mass, right? So we're going to be setting up basically a dimensional analysis problem here to figure out how much mass is getting plated, or to figure out how much time it takes to plate a particular mass. Okay, so with that said, let's go ahead and look at an example. So this first one here says that we are going to have a solution of copper 2 sulfate, which is going to be electrolyzed to plate an object with solid copper. And actually, I have given you a little picture here of that process, okay? These kind of crazy looking lines here represent our battery. Those of you that are in physics right now have probably learned that those kind of, longer and shorter lines back and forth together like that represent a battery. And so we have this Me, which represents some sort of object, some sort of metal that we're going to plate. And we're going to take the copper and lose it from this anode and plate it onto the surface of this other metal. And so it says here that we are going to run a current of 1.2 amps for 10 minutes, and we want to determine the mass of the copper that would get plated. Okay, how much copper is going to migrate from our anode to then be plated on the cathode. So, couple things. First off, they give us that value of current, our 1.2 amps. The way we're going to use that is we are going to say that 1.2 amps is the same thing as 1.2 coulombs for 1 second. Again, that's using our formula right here. Okay. Now, the other thing I'm going to need eventually is the number of moles of electrons that are being transferred. And that's where I'm going to think about my half reaction. Now, I didn't write both an oxidation and a reduction. I just wrote the reduction because remember, the copper is going to do both processes here. It's going to both get oxidized and reduced. So it's technically going in both directions, but what I really care about is this number of electrons. If I'm trying to go back and forth between copper 2, so copper positive 2, and solid copper, which is neutral copper, to go back and forth between those, I'm going to have to be transferring 2 electrons. So at some point, 2 electrons are going to be lost by the one process, and then 2 electrons are going to be gained by the other process. Okay, so with all that said, I want to determine the mass of copper plated. I want to figure out how many grams of copper. I know my time is 10 minutes. So I start off here with 10 minutes. Now, I know eventually I have seconds here as a conversion factor. Okay, so I first took the minutes into seconds. I said 1 minute is 60 seconds. Once I have seconds here, now I'm like, I need a conversion with seconds. Well, we just said this amps value is 1 second for every 1.2 coulombs. So that's what I set up here. I put my seconds on the bottom to get it to cancel and my 1.2 coulombs on the top. Okay. So now I need another conversion with coulombs that maybe gets me to electrons or to moles or something else that might be useful. Well, our only other conversion that has coulombs is right up here, our Faraday's constant, 96,485 coulombs per mole of electrons. So that's what I set up here. Again, my coulombs goes on the bottom, moles of electron goes on the top. All right, so that got us to moles of electrons, but remember, eventually I want to get to copper. So I need some connection between electrons and copper. And that's where this half reaction comes into play. For every 1 mole of copper that I'm either making or using, again, it doesn't matter which direction, it's going to be exchanging 2 electrons in order to work back and forth between the copper plus 2 solution. And so I'm going to say 2 moles of electrons for every 1 mole of copper. Well, now that I'm in moles, I get to grams by utilizing molar mass. So 1 mole of copper is 63.55 grams. So I take all of that, plug it in my calculator, and we end up getting here 0.24 grams of copper. So in that 10 minutes, I'm going to plate about 1/4 of a gram of copper onto this other object. All right. Woo! That was a lot, right? All right, I want to see if you can do one now. Okay, so the next example here is a little bit different, but very, very similar. Okay. It says here, chromium metal is plated onto an object using a chromium-3 iron solution. So again, we're going to be going back and forth between chromium that's neutral and chromium that has a +3 charge. They give us a current here of 2 amps. But this time, notice what it asks for. Here, it wants how many minutes, it wants the time that it takes to plate 1 gram of chromium. So this time, instead of going from time to grams, you want to go from grams to time. So here's what I want you to do. I want you to take a moment and pause the video and see if you can set it up. Okay? All right. Did you try it out? Did you get an answer? Let's see how you did. I'm going to put my work and answer up here. So again, 2 important things. First off, I mentioned this earlier. We're going back and forth between chromium +3 and neutral chromium, meaning there's 3 electrons being exchanged. I know I need to use that somewhere. They also told us we had a current of 2 amps. Think about what 2 amps mean. That means I have 2 coulombs for every 1 second of time. So we're going to use that as a conversion factor. Okay, so I put how many minutes equals 1 gram of chromium. Starting off in grams, I looked up the molar mass of chromium, and it's 52 grams for every 1 mole. I then said for every 1 mole of chromium that I'm making, I end up using 3 moles of electrons. That was right here. That's to get back and forth between neutral chromium and chromium +3. So then I'm going to do 1 mole of electrons is 96,485 coulombs. That's our Faraday's constant. I then am going to use my amps value. There's 2 coulombs for every 1 second. That gets us to seconds, but of course we want to get to minutes here, and so I would do 60 seconds in 1 minute. Plug all that into my calculator, and what you should have got is 46.4 minutes. I did use 3 sig figs here since my mass had 3 sig figs. Okay, so that means if I let this electrochemical cell, and specifically an electrolytic cell, since it's electroplating, if I let it run for 46.4 minutes, eventually I will have plated a whole entire gram of chromium onto some new object. All right, we've got one last problem here. Now this one uses something that I want to talk about for a second. If you look at this, it says that we have 0.2 Faraday of electrical charge. So I've given you a statement up here. Now this is not on the formula chart, so you may want to make a mental note of this. I haven't seen this type of problem very often, but it is fair game, so I thought I would talk about it. A Faraday itself, so a singular Faraday, is 1 mole of electrons that has been pushed through a wire. And again, I say the term pushed through the wire because we only see this done with electrochemical cells that are electrolytic for non-spontaneous, where I have the battery attached. And so we are pushing it through that wire. It's being forced to go, okay? And so it says here, in the electroplating of nickel, 0.2 Faraday of electrical charge is passed through a solution of nickel sulfate. What mass of nickel is deposited in the process? So this 0.2 Faraday, I'm going to interpret that as 0.2 moles of electrons that I'm trying to push through the wire in this electrolytic cell. Okay. Now, starting here actually means this work is way shorter than these other problems we did up here. Okay. If I'm trying to get to grams of nickel and I'm already in terms of moles of electrons, then all I need to do is set up a ratio of moles of electrons to moles of nickel. So I do need to think about what kind of charge change I'm doing here. Nickel itself would be neutral, but in nickel sulfate, since sulfate here is a -2, that means the nickel must have been a +2. And so we're going to have 2 electrons being exchanged for every 1 mole of nickel. So I set that up. And then, just like we did on the other problems, I went from 1 mole of nickel to 58.69 grams, which is nickel's molar mass. Plug that in to my calculator, and that gets me 5.87 grams of nickel that I'm plating in the process. All right, y'all. That was the very last example of AP Chemistry. We made it to the end. Can you believe it? I know it has been a long, challenging year, and I give you major props for making it through this college level chemistry class. I know that's insane that we've done this all in 1 year. It's crazy how much chemistry we have learned this year. I am so proud of all of the hard work that you've put in this year, and I wish you all the best of luck on the AP test. I know you are all just gonna rock it. So anyways, for the last time, if you have any questions or need any help, feel free to email me. Bye, guys. Have a good summer.